Hello, I'm Andy, I work for Etsy. My talk is called Signatures, Patterns and Trends, and it's about time series data mining at Etsy. Now, because I work at Etsy, I was going to put in some quite laboured visual joke about signature jewellery, sewing patterns and fashion trends, but I couldn't make it funny, so if you'll just pretend, then I think that will get us quite far. So I'm on the data science team at Etsy, and before I start, I'll talk a little bit about what that means, because that seems to mean different things at different companies. We're actually, in some companies, data scientists are sort of analysts, statistical modelers, quants, that kind of thing. We do a little bit of that. We've got some skills in that area, but we have separate teams that really handle the bulk of that kind of work. At Etsy, the data science team is an engineering team. We're responsible for kind of two main things, really, and I'll describe what those are separately. The first sort of area of work is what our kind of historical strengths were, I suppose. I'd characterise it as helping visitors to our marketplace find personally relevant items that they'll love. So that covers building things like recommendation engines for shops and items and users to follow, detecting trends in purchasing patterns, and trends in shop popularity and that kind of thing. We also produce some data-driven ranking factors that are used to adjust the ranks of things like search and ads and even site navigation. And we do a little bit of work around text mining in the search context, so things like auto-suggest for search queries, and here are some similar related queries, that kind of thing. Now, the other kind of strand of our work is really about building internal tools, methods, and algorithms to help apply data mining, machine learning technology on our internal data to help improve the efficiency, security, and growth of Etsy, and to help other teams around Etsy operate more smoothly. So that might include things like detecting stolen or watermarked images that people have uploaded, classifying classifiers that are similar to spam classifiers, but for detecting marketplace abuse or suspicious or fraudulent activity. We do some stuff around customer lifetime value modelling, churn prediction, and that kind of thing. And we do some stuff around detecting and diagnosing anomalies in metrics. And the system I'm going to talk about today, Kale, kind of falls into that category. All of these are collaborations with other teams, obviously, and the work that I'm presenting here has been in collaboration with our ops team. So what's in the talk? Well, first I'm going to talk a little bit about version 1 of Kale, what we tried to do with it. Actually, most of this happened before I joined the company. I've only been there 6 months, but I'm just going to say we for ease of communication. I'm not trying to claim any credit or claim any blame. So I'm going to talk a bit about what we attempted with Kale, what worked and what didn't work so well. Then I'm going to focus in a little bit on anomaly detection, because that's the area that I've been working in for most of this time period. And talk a little bit about why it's a hard problem, and why most tools, and in fact most talks and blog posts on this subject, oversimplify the issues of it, I think. After that, I'm going to present what our plans are for Kale version 2, and the first component of that called time, which I'm working on at the moment. What we're doing differently and why, a bit of an overview of the architecture, and then because I'm foolhardy or maybe a masochist, I'm going to go for a live demo as well. And then at the end, I'll talk a little bit about some lessons learned, both technical ones about the science and technology behind this, but also some organisational ones about running open source projects and making a success of those. So Kale was originally released in almost exactly 2 years ago, actually, with a talk at Velocity. At the time, it was a collaboration between our ops team and our data engineering team. And it was in 2 parts, really. So the first part was called Skyline, and the second part was called Oculus. Now, Skyline was for anomaly detection, so you would feed in metrics from servers, be they hardware metrics or software metrics or application metrics. And Skyline would flag anything that looked unusual. Basically, the idea was it would watch the graphs so you don't have to. And then the second part, Oculus, was really for kind of like diagnostic purposes, for root cause analysis. When you had an anomaly, it would enable you to search through your time series database to find other metrics which were showing the same pattern of behavior at the same time, or offset by a small amount, with the idea being, well, perhaps we can get to the cause of an issue quicker if we can see where there are correlations between different metrics from the same machine or from different machines that are tracking each other closely. Now, Kale had some quite sort of demanding goals. So the idea was, well, for a start, at the time we had something like 250,000 metrics that we were tracking with either 1 minute resolution or 10-second resolution, depending on where they were coming from. So it had to be fairly scalable. It had to work in real time in the soft sense that people mean in this industry, as in, not overnight batch jobs in Hadoop, but rather something that can actually set off an alarm basically when something goes wrong. And it had to be easy to use so that people that are on call, possibly in the middle of the night, could actually navigate through all of the metrics easily and get to the ones that are actually behind the problems. And it had to avoid having a lot of laborious per metric configuration, because nobody wanted to kind of dig through 250,000 metrics and set up each one separately. So that sounds easy, right? Actually, it turned out not to be. That, by the way, is sarcasm. Don't take that as advice. It turned out to be a little bit harder than anybody thought at the time. But it's a problem that hasn't really gone away. We're now up to about 1 million metrics in parallel with the same kind of resolution. And it's not just us that are facing this problem. So we heard on Monday about Twitter's approach to anomaly detection. Yahoo and Netflix have also both released anomaly detection packages recently. And a lot of commercial monitoring companies are including anomaly detection in their offerings. So it's a problem that's not going anywhere. And as web companies grow and they scale beyond what you can feasibly keep a handle on by putting graphs all around your ops room, it's something that we're revisiting now and seeing if we can do it better. So I'm going to talk about what went wrong with Kale and why it hasn't been such a success. But first, let's start on a positive note. What did actually work well from Kale 1? So Oculus, the time series similarity component of it, worked pretty well. And this was actually, I think, quite a win, because at the time people thought this was a very hard problem to tackle. The way it works is by taking a two-stage approach. So the first stage, you do a rough fuzzy search to basically rule out any subsequences that can't possibly match and get back a much smaller set of candidates. And then the second stage, you run a much more accurate search algorithm on those that ranks them for similarity to your known problematic sequence, your query sequence. So the special source is actually remarkably simple for this. It uses a technique called the shape description alphabet, which is a really nice hack. The way that works is it maps line segments between successive pairs of points in your time series to tokens, i.e. basically to letters based on their gradient. And in the implementation that we went for, it just uses 5 different tokens. So you've got one for steep upward slope, one for shallow upward slope, one for roughly level, one for shallow downward slope, and one for steep downward slope. You map those to letters, and then you index them with any indexing system that can handle free text. So something based on Lucene, like Solar, or in our case, Elasticsearch. Then those kind of search engines provide you with something called a sloppy phrase query, where you can actually just convert your query sequence into tokens using the same mapping procedure, and then say, search against my bank of fingerprints, or bank of signatures, if you like, using this signature as a query. You provide a slot parameter, which is the number of insertions or deletions that you're allowed while something can still match. And that provides you with kind of a rough set of results that still roughly match the query sequence. Then the second stage uses something called dynamic time warping, which is a bit more complex. I don't want to go into the details of that, but it's a time series alignment algorithm where it's kind of robust to changes of phase or to stretching and compression of one time series compared to the other, that kind of thing. It's kind of like how YouTube detects when you've used some music without permission to accompany a video, even if you slow it down a bit, that kind of thing. So that's much more CPU intensive, but the fact that you've only got a small set of candidate hits from your shape description alphabet makes it actually tenable, even on hundreds of thousands of metrics. So that worked pretty well. Another aspect of it that was quite successful was actually the user experience, user interaction side of it. So the guys that were working on it at the time were thinking very much in terms of like, get out something practical that you can understand when you're in a hurry. You know, you don't have to put a lot of thought into kind of interpreting the results. We'll provide lots of nice click-throughs so you can drill down into individual metrics. You can kind of select the metric and run a search from it. And it's all quite nice and graphical. It was designed very much with a kind of like incident management workflow in mind. So that worked quite well. But despite those two things working well, it hasn't really been a success. We're not using it internally. And as far as I know, I don't really know of anyone using it in production outside of Etsy. There's very little traffic on the mailing list, that kind of thing. I know quite a few people that have experimented with it and tried it out, but often they had problems that were blockers to further adoption. So what were those blockers? Well, the architecture was not that amenable to, let me put it this way. If anyone saw Camille's talk on Monday, there was a diagram in that called "What the hell are you building?" It kind of looked a little bit like that. So if you notice, we've got two data stores in there, Redis and Elasticsearch. We've got two separate web frameworks, Flask and Sinatra. Flask being a Python one and Sinatra being a Ruby one. We've got Rescue, which is a queuing service based on Redis, but there's also lots of like invisible components aren't really shown on here for kind of doing all these bits together and getting things in and out of the queues. We've got an Elasticsearch plugin to do the dynamic time warp search. So that's a total of 4 languages as well when you consider JavaScript that was in the front end bits of the user interface. We've got data coming in from various different sources as well. So this made it quite hard to install, even with the help of, I think we provided Chef and Puppet recipes for it, but making sure that the dependencies didn't clash with anything that you had installed already was tricky. I think this really had to be installed on several machines because even if you had a fairly small amount of data coming in, the assumption was that you would have 2 distinct Elasticsearch clusters, one for querying and one for indexing, and you would switch backwards and forwards between them. I don't really know of any open source projects that have contained this many disparate components and still been a success. I mean, you might say Hadoop, but with the Hadoop ecosystem, everything was designed to work together from the ground up. With something like this, if you release something that has this many dependencies, you sort of put yourself in the firing line of having to actually support those, which isn't always a nice place to be, especially when you actually want to deprecate it internally. And the anomaly detection side of it, which in many ways was kind of the crux of it, finding out what's gone wrong in the first place, that didn't work so well either. So the methods that the original version of Kale used, and the Skyline part, were mostly inspired by kind of traditional statistics textbooks, treatments of most of the work that's presented on the kind of anomaly detection and outlier detection in those contexts is inspired by kind of industrial production lines, that kind of thing, where you've got really fairly small tolerances, fairly consistent measurements over time, and deviations from those are generally quite easy to spot. Errors and noise are normally distributed, that kind of thing. Now, in the case of server metrics, generally speaking, you don't get normal distributions like nice neat bell curves. You get things which are, mixtures of various different distributions. You get things which kind of change distribution over time. You get a lot of spikiness and noise. And if you're basically what you're doing is kind of smart thresholding, where you're dynamically determining where to set those thresholds based on recent medians or means, then the noisier your data is, the more false positives you're going to get. Also, even if you don't have that problem, if you've got hundreds of thousands of metrics or 1 million plus metrics, well, say you've got 1 million metrics and your false positive threshold is set to like an expected number of 1 in a million, which in most statistics research, that's quite a hard restriction. Then you'd expect like 1 false positive all the time, just by dint of feeding 1 million metrics through it. So they came up with a few ways to sort of mitigate against that. So one way was to use majority voting ensembles, where you've got a bunch of different statistical tests, and you only raise the alarm if more than half of them say this point is anomalous. But if they're all kind of setting thresholds through different approaches, then they all tend to throw false positives at the same time. So that was partly effective, but not, as well as it didn't work as well as it could have done. They also used a strategy of like auto-silencing repeated alerts until they were dealt with. So you wouldn't kind of, if some metric plummeted and then stayed down, you wouldn't keep alerting on it. You would just send one when it changed state, which is that's common sense really. Another issue with this was that almost all of the methods that were in Skyline were based on detecting single point outliers. So what do I mean by that? I mean extreme values compared to sort of some period of time of recent data. But the problem is not every anomaly is a point outlier. So I mean on this graph you can see two particular spikes that are much higher than the rest of them. By the way, all of these graphs I'm going to show are from various different web errors of different kinds per minute, I believe, or possibly per 10 seconds, that I scraped out of a graphite server. But it doesn't really matter what they are. The graphs are just for illustrative purposes. So you do get point outliers when you get a sudden spike or a sudden dip, a value which is much higher or much lower than you've seen previously. But at the same time, quite often if you step back and look at more data, that becomes business as usual. I mean, if we had 10 of these graphs of the same length next to each other, who's to say that we wouldn't get 2 spikes of that size in each of those? So actually, stepping back and looking at more data might make you go, well, in fact, that's perfectly normal. I can see that happening all the time. And likewise, if we zoomed in on sort of some point in the middle of there, one of those much smaller spikes would look like an outlier compared to the data around it. So it's very context dependent. You also get a lot of different weird things happening in metric data that don't really, that wouldn't appear as point outliers, or wouldn't set off an alarm that was based on a single value being exceptionally high or low, but indicate that some behavior has changed. So you get periodic oscillations that may be kind of like part of a daily cycle of visitors to your site, or they might be on a much smaller scale, like a garbage collection cycle or something like that, or a cron job or something like that. Now, those things appearing and disappearing at unexpected times can tell you that something odd is going on. And you get cases where the extreme values, the high points and low points, stay the same, but the distribution of values between those changes. So, if we look at like the first half of this graph, it goes all the way up to like, what, 13 at the top there, but most of the values are around like, 2, 3, 4. Somewhere in the middle, something changes, but the values are still within the same bounds. It's just much more of them near the top. Now, again, that could tell you that something unexpected has happened, but if it's not going far enough away from the previous, the previously determined thresholds, even if those thresholds are dynamically adjusted, you may not realise that something's gone wrong until much later. You get cases where trends can change suddenly, like healthy growth can level off, or something that should be stable suddenly takes a dive or starts to rise. Or even something that is rising can jump around in terms of where the baseline is, like in this case. And apologies for reusing the graph, but you can get cases where events that are normally frequent become much more rare, or vice versa. So if you're expecting to see a certain type of error maybe a couple of times an hour, and you start seeing that same type of error once every few seconds, if you're aggregating by second or something, you're still not going to see more than like 1 a second, but actually the frequency of occurrence of that discrete event has seriously changed. The best thing about all of this is that usually this isn't even a problem. So if you ever actually kind of take a look through a lot of graphs, and I suspect a lot of people here probably have, weird stuff happens in them all the time when you're dealing with like lots of machines with complex dependencies, the users being fickle, and also people operating on stuff and forgetting to set, forgetting to disable an alert or whatever. Stuff just happens, there's all kinds of processes going on a machine that can affect its disk latency time or memory usage or something that may be independent of the actual health of the process on it. So you have to be a little bit clever about, I think, where and how you alert on these things. I'll go back to that in a little while. So what are we doing differently this time? Well, I've come to this from the point of view of a data scientist. A couple of people on our ops team said, we'd like to be able to make this work a bit better. We thought a lot about the processes, but we didn't think so much about the actual algorithms before. And I went, okay, let's give it a go. Let's step back, kind of turn the problem inside out and think, how can we come up with a toolkit of useful components that you can use to do time series data mining? I think actually one of the reasons this whole field has moved quite slowly with a lot of false starts is there's a big gulf between things that are written in like MATLAB or NumPy or R that are over here for kind of researchers to use, and things that are written in languages, libraries, stuff that people are happy to use in production that allow engineers that know the data and know the domain to kind of experiment on their data and try things out rapidly. So what I've been trying to do is address that sweet spot in the middle. And I've been developing a library called Time, which is essentially the first component of what will become Kale 2 at some point in the future. I'm hoping to open source it sometime in the next month or two. So it's a library of algorithms, but also a library of kind of composable pre-processing steps. It's written in Java, but it aims to be as memory efficient and cache friendly as you can get with Java. So, keep everything as far away from the garbage collector as you possibly can. Basically, it looks a bit more like C if you look at the code than Java code. It's platform and infrastructure agnostic, so I don't want to assume that everybody who is interested in this field has got, time to install 5 different components and 2 different web frameworks like Kale 1 had. But the idea is it should support kind of experimentation, prototyping, and then deployment in whatever your environment of choice is. So it's built on something called ReactiveX, which is, I only discovered recently when I was researching good ways to do this. This is a kind of stream-driven functional API. It's kind of like a combination of the observer pattern and the pipes and filters pattern, if you're into software design patterns. It came out of the .NET world, but don't let that, don't hold it against that. Don't hold that against it. It's been ported to a load of different languages, like maybe 15 different languages, all using the same kind of conceptual model, which is really useful. Netflix developed RX Java implementation. They describe it as a Netflix original. So I think like House of Cards means it's actually a remake. So what am I actually hoping to build with this? So here are what's probably going into the first release. I've thought quite a lot about pre-processing the signals to remove noise that isn't important and extract signal and features that are important. Something that people in the machine learning field kind of find is they start as enthusiastic noobs, and they go, I've got a whole ton of data, I'll throw it at the algorithm. More data beats cleverer algorithms, right? I'll throw it at the algorithm and it'll figure it all out. And then they've been doing that for a year or two, and it hasn't really worked that well. And they actually realize that most of being a data scientist is preparing data, extracting data, filtering out unnecessary stuff from data, and pulling out the useful things that you can then feed into the algorithms to give them a chance of working. So I've taken the same approach to time series mining, right? I've been inspired a little bit by how digital signal processing does this. So looking at kind of noise and signal on different frequency ranges, like wavelet decomposition lets you kind of strip out high frequency noise or extract the low frequency trends and send them to different tests. And then you've got things like fast Fourier transform, which is a good way of kind of fingerprinting the frequency information in a signal and using that to compare when two sections of a signal, see when it's changed, that kind of thing. But I'm aiming to provide, you know, a simple API of all this stuff and good examples of how to use them in practice, so you can try dropping things in and exchanging them and tweaking the knobs on things to see what works for your data. I'm concentrating on a few sort of well-known statistical tests. So generalized ESD is the same one that Twitter uses, more or less. I've taken their advice of subtracting the median from the data because it's more robust than actually subtracting the trend from the data. So if you're here on Monday, Aaron's talk kind of went into that in a bit more detail. That's for detecting point outliers. Then there's a couple of other ones, so Kolmogorov-Smirnov is really for detecting changes in distribution of data. And Mann-Whitney is really for detecting changes in like the midpoint of data, so where the mean or median falls. And I think different kinds of data will respond better to different tests. The fingerprinting and search stuff I'm going to put in pretty much as is because that worked pretty well. So I won't go into that in a lot of detail. And I'm also working on an interactive demo app, which I'll show you in a moment. But first let's talk a bit about like the design choices behind this. So why Java? I know a lot of people here might go, oh Java, everything's in Go these days, and then like next year will be, everything's in Rust these days. But like, to be honest, like Java, you know, you can build a jar file, you can drop it into any number of different platforms with a lightweight wrapper as a plugin. So, you know, we've already got the elk stack in production. Some of this stuff you might be able to do on the way in as a Logstash plugin. Some stuff you may be able to do at query time as an Elasticsearch plugin, exactly as we did in Kale 1. We're also already using Kafka for other sources of data. And we've been looking at Samza and Spark streaming for event processing or real-time processing of data. Now, if it gets to the stage where we want to do like really heavyweight computation that isn't so urgent, but you know, we can tolerate an overnight delay or a delay of a few hours, then most of what my team does uses Hadoop and Scalding, which is a Scala library for building Hadoop workflows, and Conjecture, which is our machine learning library based on Scalding. And I think it would be very easy to drop a lot of these techniques into Hadoop as plugins for Scalding or Conjecture. And Android, I mean, I put that in kind of as a joke, but there's a serious point behind it, which is none of this stuff is necessarily restricted to being useful for server metrics. And, you know, Internet of all the things, right? Sooner or later, there's going to be a use case for actually monitoring what's going on a device and doing the data processing on that device rather than having to ship it all to some, you know, central point via Wi-Fi. You could use this stuff for earthquake detection or, you know, building a burglar alarm if you really wanted to. And there are a lot of other kind of event databases and time series databases that are based on Java. So it should be fairly easy to write wrappers for time components and drop them into those as necessary. Also, there are a lot of maths and stats resources available. Like, I wasn't going to try and rewrite Kolmogorov-Smirnov in Go because, well, I don't know Go and I'm not that great at statistics. But you know, Java's got a lot of things available that may not always necessarily be the fastest or most production ready, but it's much easier to take, say, Apache Commons Maths implementation of the Kolmogorov-Smirnov test and tune it so it's less wasteful and doesn't allocate memory it doesn't need to all the time, rather than rewriting it from scratch in a new language. I thought about Scala, but Java's more widespread. It's generally faster when you're doing low-level number crunching stuff. It'll be easier for people outside Etsy to adopt as well, I think, in general. So ReactiveX, let's talk a little bit more about that, because I think it's quite interesting. It fits this sort of problem really well. The design pattern that it embodies is called functional reactive programming. So it's kind of event-driven, you build pipelines of components that all sort of follow a similar interface. So the idea is when some data arrives, it gets processed by a component, calls the next component, and it does all the orchestration and plumbing of that stuff for you. So if you implement all of your things as operators in the ReactiveX framework, they just have to fulfill a couple of interfaces, and you can kind of chain them together in pipelines very easily. And there are, even if you're using RxJava, you can write a component in another language if you want, like using idiomatic Java 8 or Scala or Clojure or whatever, and drop it in as another jar file. As long as it follows the same kind of interface, then it'll all fit in quite easily. So by combining these together in pipelines, you can do things quite easily that let you experiment with different pre-processing stages and then different statistical tests on the output of those stages, rather than trying to fit everything through a kind of one-size-fits-all pipeline. Like I said, I'm a bit of a glutton for punishment, so let's see if we can get a quick live demo of that working. So, the font size is a bit crazy. This is a demo app that I've developed. Never mind the font size. So basically, what this does is it listens to the microphone on my laptop and uses that as a proxy for data coming out of the server. And then it lets me build up a pipeline quite easily of different components that fit together kind of end-to-end like Lego, because they all have this observable of type double interface. And actually, let me start it going while I talk. What that will do is, as I'm talking, it'll listen to the microphone, and it will take an average volume reading every few milliseconds and plot that on the graph. And that is then passed through a statistical test called a Kolmogorov-Smirnov test. Now, it has to build up kind of a library of recent data to compare it to first, so you won't see any output to begin with. But after I've been talking for a little while and it's built up a few of those, it'll start printing some numbers to the console down here. Those numbers are p-values, so what that means is the lower the number is, the more unusual the last chunk of data that it's read from the microphone is. So it's building up sort of a library of, I think, 10 first. So when a new one comes in, it compares it to the previous ones, say, okay, how unusual or typical is this recent time series that I've just read off this metric? The metric could come from anywhere. I'm just using the microphone because then you can test it without having to have a live connection to a server, and people can try it themselves to see what it looks like. So the p-values are starting to come out. So 0.1 means, there's nothing particularly unusual about it. But then if I do something odd, like I suddenly go quiet, right, it's printed with the bottom there. And similarly, a load of applause has also caused it to kind of to alert as well, because that's pretty unusual in the middle of a live demo, I think. And there are other ways you can trigger it. It's not just based on thresholds. So maybe if I just sort of put a constant noise into it, like, there you go. So it's actually detecting variation or lack of variation in the signal, and not just kind of alerting when it's gone outside the threshold. You'll notice it's centered around 0. That's on account of one of the steps in the processing chain called wavelet filtering. So what I've done basically is only taken the highest frequency components of the signal, so it's removed the underlying trend and removed any sort of slow variation in like a noise getting louder or softer slowly, and only kept the kind of spiky roughness. It's using changes in the distribution of that to indicate that something's gone wrong. There's lots of other ways to do that, but that's one way that works quite well. So yeah, this isn't out yet, but I'm just putting finishing touches to the tutorial and demo app, and kind of rounding off a few rough edges on the API. So I'm hopefully, once conference season's over and things are a bit less hectic, watch this space. So let's have a quick recap. What have we learned? Well, we learned you've got to keep your architecture simple, especially if you're going to come up with an open source release that's supportable and that people will actually adopt. The variety of tools in the messy Kale 1 diagram, each of those individual choices actually makes perfect sense. Like choosing Python for part of it was because there are a lot of good maths libraries for Python, for example, but when you compare that to, well, we're already using Ruby over here, it's like a really good idea. So something being a good fit for a problem doesn't always imply, let's say, add that new piece to our stack. There's a bit of a meme going around at the moment that an ex-Etsy engineer called Dan McKinley came up with, which is choose boring software. And the way I like to put it is, solving interesting problems with boring software is much better than solving boring problems with interesting software. So be careful about open sourcing a platform or an application that you're not actually using in production, or you haven't been using it for some considerable length of time, so you know that it's a keeper rather than something that's at risk of going tits up, as we say in Britain. I don't think this really applies so much to a library, which is why I'm approaching the problem from this angle partly, because if I provide a set of tools and they do what they say on the tin and there's no horrible bugs in them, then even if we end up not using that library internally, it doesn't have the same support load as a all-in-one platform. So we've also, anomaly detection is more than just outlier detection. So like a one-size-fits-all approach to this thing probably won't fit at all. You'll have to think a bit about what kinds of unexpected behavior you're likely to see. Although it is possible using some filtering, as we saw in the demo, to pick up different kinds of anomalies from the same pipeline if you do a bit of careful feature extraction first. And this is something that a lot of people have touched on this week, which is not all metrics should result in a pager alert if something goes wrong. In this case, not all anomalies should result in a pager alert. The way I'm thinking about deployment for this stuff is, it's probably best to actually alert on anomalies that are in business critical or user-facing metrics, like things that you A/B test on, like sign-ups, conversions, page load time, bounce rate, that kind of thing. If you have an anomaly in one of those, hell yeah, definitely report on that. Scan everything else for anomalies, but then use that information for root cause analysis when you've got an anomaly in something that actually affects people. But don't necessarily send an email or a page every time a metric goes a bit weird, because it will happen. It just happens all the time. So yeah, good UI and workflow is going to be really critical for getting stuff into production. I think Kale 1 was a bit of a victim of its own success, because everyone went, that looks really cool. Yeah, oh, that's really easy to use, fantastic. But actually it turned out that the UI kind of wrote checks that the algorithms couldn't really cache. Ensemble methods and auto-calibration and that kind of thing are a really good idea, and we're hoping to kind of spend a bit more time developing the ideas from Kale 1 and making them a bit more extensible. And you can do similarity search as well, so I think that was quite a useful win for using quite a pragmatic approach to filtering the data. And that's kind of it, really. Watch this space for more news. Thank you. Yeah, we've got time for questions if anyone's got any.
Yeah, your demo, you gave it a few seconds to sort of establish a baseline. How long does it take until the anomaly, like if you being silent, becomes sort of the new normal? Like when would that have not been an anomaly?
Well, in this case, it was using a fairly crude technique. So it uses like the last 10 windows of data, like what you saw on one graph. It uses the last 10 of those. So if you stayed silent for like more than 2 of those, it would go, okay, I've seen one of those before. You have to think a little bit about the best way to provide those reference chunks. So actually in real usage, what you might want to do is not only just provide recent ones, but provide like from this time yesterday or this time last week, that kind of thing. But that kind of thing, like when to do auto-silencing and when to sort of, how to handle ones with detected anomalies in, that's I think there are lots of strategies to that, and one way might be, if you've got something that's anomalous, then exclude that from the set that you use for reference with a flag. Right? It's the one over there.
So, is mostly focused right now on getting the anomaly detection part solid and usable as a product. Is the next big component on the roadmap doing the multi-metric correlation aspect that Kale 1.0 had?
Yeah, so I've thought quite a lot about this. Well, I say quite a lot. This is kind of, I think this is like the next logical next step is like looking across the same metric across a cluster of machines, or looking at related metrics on one machine and using deviations from those to indicate when the anomalies happened. So one fairly simple way to do that, instead of using like the last 10 windows of data necessarily to compare the most recent chunk to, you could use 10 consecutive windows that are happening at the same time on different machines and see if any of those are outliers with regard to the others. But yeah, I think that's an area that's going to require a lot more trial and error, or research as we call it in data science. Yeah, once we've got some of the components out there and working okay on the simple stuff, I think that would be much easier to figure out the right strategy for like large clusters and that kind of thing.
Are you also planning re-architecture with respect to all the components, the Python, Ruby, the Elastic, stuff like that?
Yeah, so what I've been thinking is, and this is something that, you know, there's a lot of conversation still to be had, is we've actually been thinking about concentrating on the ELK stack, because a lot of people are already using it, and you can split up the workload, as I said, between stuff that runs as a Logstash plugin to do kind of fingerprinting or feature extraction on the way in, and stuff that happens on query time, like doing a similarity search, or actually running the statistical tests. You know, Elasticsearch isn't the time series database, but in the same way that, that Druid is kind of an event database, but you can store data in it that constitutes a time series. You can kind of do that with Elasticsearch as well. It may not be as efficient as a dedicated time series database, but it's, you know, well understood technology. Loads of people are already using it. But I'm hoping that this is all kind of like lightweight enough that people can write wrappers for other environments fairly easily. And like ReactiveX isn't a heavyweight library. People use it on Android for processing kind of event streams from a UI, so I don't think it would be difficult to kind of drop it into other platforms. And I'm happy to kind of help people get their heads around how to do that. Anybody else? Cool, well come find me during the break if you do want to talk, or ping me on Twitter or whatever. Follow us on GitHub for more news. Thanks.